Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schuller at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about convolutional autoencoder. So let's get started. A so-called autoencoder is a neural network with unsupervised training, which means that we don't need to supply a target function. There is only a training set, which is also the target set. A convolutional autoencoder uses convolutional neural networks. An autoencoder maps the input signal to a lower dimensional representation using its encoder part. In this way, it is similar, for instance, to an audio encoder, which compresses an audio signal into a representation with fewer bits than the original audio signal. I invite you to take a look at another course offered by Professor Schuller at the Ilmenau University of Technology. It's called Audio Coding. We also have many Jupyter notebooks and tutorials that you can find here on the GitHub and on a YouTube playlist. The decoder part of an autoencoder maps the lower dimensional representation back into the higher dimensional representation. And this is similar to an audio decoder, which decodes the compressed version back to an audio signal. The reconstruction after the decoder part should be as close as possible to the original. Hence, the original training set is also the target. In our Python example, we simply use a 1D convolutional layer for the encoder, and this corresponds to the analysis filter bank of an audio encoder. And if you're interested to know about analysis filter banks, synthesis filter banks, and filter banks in general, we also offer a course. It's called Multi-Rate Signal Processing, offered by Professor Schuller at the Ilmenau University of Technology. And you can find, again, Jupyter notebooks with interactive examples and embedded video tutorials from our YouTube playlist. But going back here into this Python example, where we use a 1D convolutional layer for the encoder, we also use an activation function. And in this case, we use the 10H function, which seems to work better than the sigmoid in this application, probably because it keeps the signs. We will use a stride or a downsampling factor of n equals to 1024 and filter kernels of size 2 times n. To obtain the same dimension as the input at the encoder output, which is a critical sampled filter bank, we need n filters or n output channels. But because we want to reduce the dimensionality after encoder, we choose a lower number, which makes it an over-critically sampled filter bank. For instance, with out channels equals to 32. This is similar to an audio encoder, where we simply drop the filter subbands with the highest frequencies. We will still have to choose the padding, meaning the number of zeros which we pad before and after our audio signal before the convolution, or rather correlation in pytorch. To align the output of the decoder with the input signal for the case of symmetric filter kernels or impulse responses, we need a padding of the filter length divided by 2 minus 1, or the kernel size divided by 2 minus 1, because then the filtering starts with the first sample at the center of the filter, which corresponds to the position where the filter outputs the correspondingly filter sample for both encoder and decoder. Hence, in Python, our encoder convolutional layer becomes this here. So we will have the number of in channels equals to 1, the number of out channels equals to 32, the kernel size equals to 2048, so it's 2n. The stride will be 1024, and padding will be the kernel size divided by 2 minus 1. and we use bias equals to true. Observe that we have one input channel, the audio signal, and 32 output channels, the subbands. For the decoder part, we need a synthesis filter bank, which in neural network literature is also called a transposed convolutional layer. And in PyTorch, we can use the conv transpose 1D. Therefore, we will have our conv transpose 1D that has in channels equals to 32, out channels equals to 1, the kernel size equals to 2048, the stride equals to 1024, and padding equals to 1023. So we can see that it's the same kernel size, the same kernel, and the same padding as we used for the conv1D. Observe that for the synthesis filter bank, we have 32 input channels, the subbands, and one output channel that will give us the reconstructed audio signal. The function for the encoder is now given here. So we will have our conv1D layer given here that we're calling conv1. Then we will use the 10H like we mentioned before, and then we will return the output. Observe that here we included the 10H activation function, which can also be seen as a range limiter between -1 and 1. For the decoder, we have this function here, where the X reconstructed is the synconv1 that is defined here as using this conv transpose 1D. For both together, it becomes the overall autoencoder. And we have the encoder, the decoder, and we will have the output is the reconstructed signal. We will put these functions into a class called conv-autoencoder. For the training, we use the input signal also as a target. There, we have to limit the length to the signal length produced by the output model, which we can simply obtain by letting the model run once before the training. Here, y is the target signal with the same length as the output, the model output. As a loss function, a common choice is to use the mean squared error, even though it might not be optimal, but we will try out in this example. The training then can be done in a for loop, and we have a certain number of epochs, and then we will have the predictions generated by applying the model to our input. We calculate our loss, then we will just print the loss every epoch divided by 10, and then we will also need to, in every step, to use the zero grad into the optimizer. We use the backward to the loss, and we use this step into the optimizer.